Now we have the Bohr model of atom. Like after studying the drawback of Rutherford, there was a new model which was being given, that is the Bohr model of atom, and it could explain almost, you can say, many phenomena. See, according to this, atom is spherical, right, in which in the center there is a nucleus which is positively charged because it contains protons and neutrons. Right. As far as their charges are concerned, proton is positive charge and neutron has no charge. Got it? In center there is a nucleus. This is nucleus which is positively charged because it contains particle proton, neutron, proton with positive, neutron with no charge. Outside it there are certain shells present like this, and these shells are being named as K, L, M, N, so on. So for K shell, this is the first shell, for L being 2, M 3, so on in this way. And in these shells the electrons are present. In these shells the electrons are present. For example, if I need to draw a model, atomic model for the sodium, I know the configuration is 281, because as far you have done in the 9th or the 10th standard, you know this kind of configuration. But otherwise later in this chapter I will just tell you that we no longer write configuration in this way, we write in a different pattern. But when we are talking of like about this movement, so you know that how the criteria to write the configuration is just to look at the number of protons, number of electrons, and you just distribute them in among the shells by following the formula, that is 2n square. So if I try to fill the electrons according to the sodium atom, so in the first shell it is 2 electrons, in the second it is 8, and in the third it is 1 electron, right, if I just see for the sodium case. So this is being discussed by the Bohr, and there are certain many other things which have been explained. I am going to just take it one by one. So this is the you can say a general concept which you must be familiar in the lower class. So we are going to just elaborate it in a perfect manner, and you know that as far as we have not talked about the charge of the electron, it is negative. So this is what we are going to do now. See, atom consists of small heavily positively charged nucleus. This we have done. You know that there is a positively charged nucleus in the center, and around it the electrons revolve. We know this also. Second, outside nucleus there are shells which are named as K, L, M, N, you know that, and which electrons revolve. You know this also. You know that these shells are also called as energy levels. They are also called as energy levels. You know that why they are called as energy levels? Because they have fixed energy. They have fixed energy. This point we will take later, right? So if we want to talk about the energy of the electron in each orbit, because it is called as shell also, it is called as orbit also, it can be called as energy level also, one mean the same. So if you need to look about the energy of the electron in any orbit, so there is a formula, that is E is equal to 2 pi square me4 divided by n square into h square. N means number of orbit, that means you want to look for the energy for the first orbit or second or third. 2 constant, pi you know 22.7, mass you already know, E you know that charge on electron, n square again the number of shell, h you know the Planck's constant. So if you just try to solve it, then we have the solved value also, that is En is equal to minus 21.8 into 10 raised to power minus 19 divided by n square, particularly in joule per atom. How I derived? I just put the values here and I got this value solved for you in terms of joules per atom. But if I need to see them in electron volt per atom, so it comes out to be minus 13.6 upon n square, and in kilojoules per mole it comes out to be minus 1312 upon n square kilojoules per mole. So that means you know that the orbits are there, and you can also find the energy of the each orbit also. Then we can also know about the radii of orbit. Now what is the formula for that? It is Rn, that means R of any orbit whose radii is unknown or you want to know, it is equal to A naught into n square, where A naught is 52.9 picometer. And for hydrogen like atoms we divide it by an atomic number also. So it becomes Rn is equal to A naught upon n, A naught into n square, just need to divide by Z. Moreover, you can know the velocity of electron also. The formula is Vn is equal to V naught upon n. Again, n means in which orbit you need to know the velocity of the electron. And for hydrogen like, you need to multiply with their atomic number. And V naught value is 22.188 into 10 raised to power 8 centimeter per second. So that means all these kind of information you can get. You can know the energy of the orbit, you can know the velocity of the electron in that given orbit, you can know about the radius of that orbit. So this is the second postulate of the Bohr model. Third is that they say that energy of electron is quantized. Energy of electron is quantized. When I say quantized, it means it has certain set values. It has certain set values. Like you must have made a STD call to some of your distant relative, then how the meter works in that case, like how the cost of that calls come. It is you can say it is initially 1.50, then it doubles, it becomes 3. So that means it occurs in the multiples. So likewise, the energy of electron is quantized. That means it has definite set of values in which the electron's energy is being seen. Next is that it's not like that any orbit which you draw can make it 1, 2, 3. No, we cannot. Only those orbits are permitted in which angular momentum of electron. What is angular momentum? This is mass into velocity into radii. Angular momentum of electron is integral multiple of h upon 2 pi. So this is the mathematical expression that when these two terms like when the angular momentum becomes equal to the integral multiple of h over 2 pi, in only that orbit can be made as k, l, m and so on. So that means it's not like that any orbit you can imagine that may exist. Only that orbit exists where the angular momentum of electrons comes out to be integral multiple of h upon 2 pi. Next, when the electron is in lowest state, that is called as ground state. Like this is this one electron, the ground state of this electron is the M shell. So you can say the initial state of the electron is called as normal. It may be called as normal also, normal or the ground state. And you know that whenever the electron is in ground state, it neither release nor absorb energy. So that means it is a stable state. But when the electron energy absorb energy or give energy, it gives during excitation. Like suppose you have an electron like this. Let's say electron is here and there is one more orbit out. So if you supply this electron with energy greater than its energy of the orbit, again let's say that the energy of electron here is A and you are supplying the electron with the energy B. Let's say energy which you are supplying is greater than the energy of the electron. Then it will absorb that in this energy and it will get excited to higher energy level. It will jump to a higher level. This process is called as excitation. So it gets excited to the high energy level. Then what happened? It remains here for a certain period of time, but excited states are always unstable. Excited states are always unstable. So ultimately it returns to its original shell, and when it does like this, it just release the absorbed energy. Let's say here the energy, let's say it is if E1 and this is E2, so it absorbs E2 and get excited to the high energy level, but excited state being unstable, it is ultimately going to return to its original level, and when it does, it just liberate the energy which is being absorbed by it. But if you are supplying it energy, suppose E2, suppose we take a case where E2 is less than E1, then nothing is going to happen. If you need to cause an excitation, there has to be energy which you are supplying should be more than the energy of the electron, then only it will jump to a higher state. That is the excited state, and moreover it is unstable, it is going to revolve there for a certain period of time, and then ultimately it will return to its original state, and when it does, it just release the absorbed energy. So this is all about the Bohr you can say model of atom. I think you got it. First you should know that where the nucleus is there, where are the shells, how they are named, and where these protons, electron, neutrons are being arranged, because this is again an important fact, because when we studied the when we studied that Thomson model, the major drawback was that he could not show the distribution of charges. So it can be it is clearly done by the Bohr model. And moreover, you come to know about the many information related to the orbit, the energy, the radius, the velocity of an electron. And if you talk about energy of electron, it is quantized, and moreover, which orbit is permitted, you know now, and what is ground state and what is an excited state and what is the difference. So this is all explained by the Bohr model. Otherwise, when we took into consideration that Rutherford, then there was a point which could not be explained by Rutherford, because in that the major drawback was that because they said that the electron is revolving around a nucleus, and they said when any charged particle revolve, it radiate energy, so it should also spiral, should shorten its path, spiral down into nucleus. But it is well explained by the Bohr, as he said that when the electron is in its ground state, it is neither absorbing nor releasing, so there is no that point that reflects the behavior of electron in this. That means it will not spiral down or it will not shorten its path, and it is not going to fall into the nucleus. So this is all about the Bohr model of atom.